Welcome you all in the lecture number 15 of Engineering Mathematics 1 MTL 1025. In this lecture, we will going to discuss Taylor series expansion of function of two variable, expansion of one polynomial, and what are the conditions for maxima and minima for function of two variable, right? So let us start with one example. Taylor series expansion of function of two variable f of a plus h and b plus k is equal to f of ab plus h dou f by dou x k dou f by dou y 1 by factorial 2 h square dou 2f by dou x2 plus 2hk dou 2 by dou x dou y of f plus k square dou 2f by dou y2 that is 1, right? This is the formula for Taylor series expansion of function of two variable. Okay. Now we have to expand one polynomial. Earlier we have seen many functions which we expand by using Taylor series. Now see this. Then let us assume that this is fxy, x square y plus 3y minus 2. The problem says that we have to express this polynomial in power of x minus 1 and y plus 2. We have to expand this in power of this using Taylor series. Okay. In which power we have to expand? X minus 1 and y plus 2. Okay. Let us see our formula. What is our formula? Our formula is a plus h is equal to, in which power we have to expand? X minus 1 and y plus 2. Then this is h and this is k. Okay. H is this and k is this. Now, if h is equal to this, then what are the point? A is equal to 1. And if k is equal to y plus 2, then what is the point B? B is equal to minus 2. It means our point is 1 and minus 2. Okay. The formula says that evaluate the value of the function and its derivative at the point AB. Then what is f of AB? Means f of 1 and minus 2. This is equal to 1 square into minus 2 plus 3 into minus 2 minus 2, right? That is minus 2 minus 6 minus 2, that is minus 10, this thing, right? If f of xy is this, then f of 1 and minus 2 is this. Now derivative of this f with respect to x, right? Partial derivative of f with respect to x. Partial derivative of this thing is 2xy, partial derivative of 3y is 0, and partial derivative of 2 is 0. Now putting x is equal to 1 and y equal to minus 2, then this gives us minus 4. Derivative of f with respect to y, that is x square plus 3. Putting x is equal to 1 and y equal to minus 2. Here no y term, putting x equal to 1, this is 4. Okay. Now dou 2f by dou x2, differentiate this again with respect to x. Dou 2f by dou x2 is equal to 2y, right? Then putting y is equal to minus 2, this is minus 4. Now dou 2f by dou x dou y, okay, this is 2x. Putting x is equal to 1, this gives 2. Dou 2f by dou y2, okay. What is dou f by dou y? Dou f by dou y is x square plus 3. Again differentiating this with respect to y, that is 0. Okay. What is third derivative with respect to x? Dou 2f by dou 3f by dou x3. Differentiate this. This is 0. Okay. Now dou 3f by dou x2 dou y. This is 2. Differentiating dou f by dou 2f by dou x2 with respect to y. What is dou 2f by dou x2? This thing. Again differentiating this with respect to y, that is 2. The value of this at point 1 and minus 2 is 2. Okay, similarly dou 3f dou x dou y2 is 0 and dou 3f dou y3 is 0. Okay. So this table gives us value of the function and its derivative up to third order, right? And fourth order onward derivative, all derivatives are 0. Okay. Now use this formula. What we have to do in this formula, replace h by x minus 1 and k by y minus 2, right? And a is equal to 1 and b equal to minus 2, right? Then this is f of ab, h dou f by dou x is minus 4. This is dou f by dou x. K y plus 2. Dou f by dou y is 4. Okay. 1 by factorial 2 h square. This is h square. Dou 2f by dou x2. What is dou 2f by dou x2? Minus 4. Now 2h k and dou 2f dou x dou y. Dou 2f dou xy. This is 2. K square. Dou 2f by dou y2. Dou 2f by dou y2 is 0. Okay. 1 by factorial 3. H cube. Dou 3f by dou x3. This is 0. 3. H square into k. 3 h square k into dou 3f dou x2 dou y. Dou 3f dou x2 dou y is 2. Right? And other terms are 0. Since derivative is 0, so other terms is 0. Now simplifying this. First term is x minus 10 and second term is minus 4 into x minus 1 and third term 4 into y minus 2. Simplify this, right? This is minus 2x minus 1 whole square plus 2x minus 1 y plus 2 plus x minus 1 whole square into y plus 2. If you simplify RHS, right, then you find this. Okay. Then how we obtain RHS? Using Taylor series expansion. Okay. Now let us discuss the maxima and minima. Okay. Now let us see the maxima and minima, right, for function of two variables. Before going to two variables, we will discuss about the function of one variable. Let us consider y is equal to fx. This is function of single variable and see the graph. Okay, see this point. This point is x is equal to a. Ex equal to a. Consider its neighbor point. Its neighbor point is a plus ah, f of a plus h, right, minus. If f of a plus h minus f of a is greater than 0, then this a is point of minima. Okay, and if f of a plus h, suppose our a is this, or b, say b is this, and b plus k is this, then f of b minus f of b plus k, right? What is f of b? F of b plus k. This is greater than 0, or you can say that this minus and plus, this is less than 0. Then b is point of maxima. Okay, such b is point of maxima, right? Same concept we will apply for function of two variable. For example, if function of fxy, then what is the point ab? If this is maxima, minima, or saddle point, then we have to check that what is the value in its neighboring point, means function value at a plus h b plus k minus f of ab. If this is less than 0, then ab is point of maxima. If it is greater than 0, then AB is point of minima. If neither less than 0 nor greater than 0, then it is saddle point. Okay. See how we find these conditions. This thing for maxima and minima are function of two variable, which is different from the maxima and minima are function of single variable, right? For single variable, we know that dy by dx is equal to 0, and from here we evaluate the point, and d2y by dx2 at that point. If this is less than 0, then this point is maxima. If it is greater than 0, then this is point of minima. Okay, but here we are discussing about the function of two variable, so this concept is somehow different with the function of single variable. Not different, but our graph is different, right? In single variable we can easily see this, and in two variable function z is equal to function of xy, and you have to plot, right? Three-dimensional plot, and in three-dimensional plot you have to visualize that. Okay, now let us see what we will do for function of two variable for maxima and minima. See, if f of a plus h and b plus k minus f of ab is less than 0, then this point is maxima. Okay. If f of a plus h b plus k minus f of ab is greater than 0, then this point is minima. Okay. Now, what is f of a plus h b plus k? That is f of ab. H dou f by dou x, k dou f by dou y at ab. 1 by factorial to h square dou 2f by dou x2 plus 2hk dou 2f dou x dou y plus k square dou 2f by dou y2. Okay. Now, f of a plus h b plus k minus f of ab, right? Take it in right hand side. We got this term. Okay, we got this term. Now this is equal to h into dou f by dou x, k into dou f by dou y at ab, and 1 by factorial 2 plus similarly third order term. This is at ab. But see, what is h and k? We are saying that a small neighborhood of ab. A small neighborhood means what? H and k are very small, right? If h and k are very small, then what is h square and k square, right? They are more less than 1. Okay, so these type of term we can neglect, right? Neglect all those terms of equation 1 where h square and k square appears. Okay, then this is second degree term and second degree term, so neglect this term. Okay, neglect this term. Then f of a plus h b plus k minus f of ab is equal to h dou f by dou x plus k dou f by dou y at ab. Okay, it means it's a sign. It's a sign. Depends on this sign. Okay. Now see. For a small value of h and k, the second and higher term is still smaller. Hence, these terms are neglected. Okay, that we already explained you. Now see. LHS of second equation, right hand side says that f of a plus h and b plus k minus f of ab is equal to h dou f by dou x plus k dou f by dou y at the point ab. Okay, then if this is positive, then this thing is positive. If this is negative, then this is negative. Okay, but we know that for function of one variable, for maxima and minima, first derivative is 0. Okay, so in here our first derivative dou f by dou x and dou f by dou y, this is equal to 0. For maxima and minima function of two variable, this is necessary condition. Okay, dou f by dou x and dou f by dou y is equal to 0. This thing, right? For maxima or minima, at any point, the first order partial derivative of a function is 0. Okay, then solve this, we got x is equal to ab. Okay, then if this term is 0, then what is equation number 1? F of a plus h b plus k minus f of ab is equal to, since first term is 0, this term is 0, so the second terms remains, and this is equal to 1 by factorial 2 h square. We call it this notation, say r, and this second order partial derivative is s, and this derivative is t. H square r 2hks plus k square into t. Okay, now you manipulate this term by adding and subtracting subterm. Say 1 by factorial 2 h square r is this, 2hks, s is this, k square t is this, means r is dou 2f by dou x2, and s is dou 2f by dou x dou y, and t is dou 2f by dou y2, right? Then what is the sign of this term? Basically this is equal to f of a plus h and b plus k minus f of ab. We have to see whether this term is greater than 0 or less than 0, right? Then this is equal to 1 by factorial 2h square r 2hks plus k square t. Okay, now see, what is this? Okay, the sign of this term depends on this term. Then what is sign of this? Multiplied by r and dividing by r, right? We want to simplify this term. Then sign of this term, what is this term? We have added this k square s square and subtracted this. Then this is equal to rh plus ks whole square. Okay, this thing, and this term is equal to k square rt minus s square. See, this term is always positive. This term is always positive. 1 by r hr plus ks square, and this is k square rt minus s square. Okay, 1 by r k square rt minus s square. Okay, the sign of this, but the sign of this term depends on sign of r and rt minus s square. So we assume that rt minus s square is greater than 0, right? If this thing rt minus s square is greater than 0, if this is greater than 0, then this whole sign, right? If rt minus s square is greater than 0, then the sign of this depends on r. Sign of this depends on sign of r. Okay, now see, if rt minus s square is greater than 0, then say if r is greater than 0, rt minus s square is already greater than 0, then sign of this is greater than 0. It means our LHS, that is f of a plus h, f of a plus h and b plus k minus f of ab is greater than 0. Since r is positive and rt minus s square is positive, it means r is greater than 0 and rt minus s square is greater than 0, right? It means this is greater than 0. So AB is point of minima. Okay, what is this? Point of minima. Next, if rt minus s square is greater than 0 and r is less than 0, then this thing f of a plus h b plus k minus f of ab, this is less than 0, and in this case ab is point of maximum. Then what is the conclusion? Conclusion is that rt minus s square is greater than 0 and r is greater than 0. AB is point of minima, and if it is greater than 0 and r is less than 0, then this AB is point of maxima. Okay. So, and another condition, if rt minus s square is less than 0, then what happen? Then LHS means this thing, right? Sorry, LHS means this thing, f of a plus h and b plus k minus f of ab, this is LHS. Then LHS, this thing changes his sign with hk. Why? See this thing, RH plus sk, this is positive, k square is positive, and rt minus s square, what is rt minus s square? Rt minus s square is less than 0. Okay, this is less than 0. It means 1 by factorial 1 by r rh plus sk whole square plus k square rt minus s square. This thing is less than 0. This thing is greater than 0. Okay, right? So the sign of these total things, it depends on hk, right? Since the value of, remember that since the value of r, s and t are fixed at any certain point, okay, so this whole things depends on the sign of hk, right? So in this case we cannot decide maxima or minima. Okay, that is AB is the saddle point. It means, what is this case? This AB is saddle point. Okay, now come to the third case. If rt minus s square equal to 0, if rt minus s square equal to 0, then what happens? This thing is 0, and then this term becomes 1 by r rh plus sk square, right? If this is equal to 0, then what is this? H by k is this, right? But it is possible that h by k is minus s by r. It is a doubtful case, right? This case is doubtful case. Now let us consider one example. Working principle for maxima and minima are as follows. For a given function fxy, we have to consider dou f by dou x, dou f by dou y, dou 2f by dou x2, dou 2f by dou x2y, and dou 2f by dou y2. Okay, we have to consider all these partial derivative, and for necessary condition put dou f by dou x equal to 0, dou f by dou y is equal to 0. From these two evaluate the point. Solve these two equations. find out the point. Okay, at this point you have to find out what is rt minus s square. If rt minus s square is greater than 0 and r is less than 0, then this function has maximum value. Rt minus s square is greater than 0 and r is less than 0, then this function has minimum value, right? If rt minus s square is less than 0, then this function has neither maximum nor minimum. If rt minus s square equal to 0, then it is doubtful case. Okay, then we will move to the third derivative. Now let us see one example. See, if fxy is equal to this, if fxy is equal to x square y square plus 6x plus 12, okay, then find the maxima or minima. For maxima and minima, for at which point? For this we have to evaluate dou f by dou x is equal to 0 and dou f by dou y is equal to 0. Okay, see, what is dou f by dou x? Dou f by dou x is equal to this. Okay, this is dou f by dou x. Our function might be not correct. X square plus y square plus 6x plus 12. Yes, the function might be not correct. Correct this function. This is fxy is equal to x square plus y square plus 6x plus 12. Okay, this plus sign is here. So fxy is equal to x square plus y square plus 6x plus 12. So evaluate dou f by dou x. Dou f by dou x is 2x plus 6. What is dou f by dou y? That is 2y plus 0. Okay. Now dou f by dou x is equal to this and dou f by dou y is equal to 0. Then 2x plus 6 is equal to 0 and 2y is equal to 0. Solve this. X is equal to minus 3 and y is equal to 0. What is our point? Minus 3, 0. Okay. Now rt minus s square. What is rt minus s square? First see what is r. What is r? R is equal to dou 2f by dou x2. What is dou 2f by dou x2? What is dou f by dou x? Dou f by dou x is 2x. Okay, this thing is plus. Dou 2f by dou x is 2x plus 6. Then dou 2f by dou x2 is 2. Now yes, dou 2f by dou x dou y. Differentiating this with respect to y, that is 0. And t, dou 2f by dou y2. This is again differentiating this term. Right, dou f by dou y. What is dou f by dou y? 2y. Then dou 2f by dou y2 is 2. Okay. Now rt minus s square at the point minus 3 and 0. What is r? R is 2. What is t? T is 2. What is s? S is 0 square. Since this thing does not containing any xy, so no need of this point. Okay, this is equal to 4. What is sign of 4? This is greater than 0. Okay, this is greater than 0. Right, 4 is greater than 0. It means rt minus s square is greater than 0. If it is less than 0, then this point is saddle point. Okay, if rt minus s square is greater than 0, then check the sign of r. What is sign of r? What is r? R is equal to dou 2f by dou x2, that is 2. Since r is greater than 0 and rt minus s square is greater than 0, so this point minus 3, 0, rt minus s square is greater than 0 and r is greater than 0. So this point is point of minima. It means minus 3 and 0 is point of minima. Okay, this is point of minima. This is one of the simple example of maxima and minima. In next class we will discuss about the remainder term of the Taylor series and some more problems of the maxima and minima. Okay, thank you.